Hi all, welcome back to Computer Organization course. We'll get started. Your second chapter is Machine Instructions and Programs. So this is the marks split up for this chapter. The first thing what we'll study here is memory locations and addresses. So what is a memory? Memory is used to store information. The information can be number, character operands as well as instructions. Let's see what is the operand. Okay. Suppose if we have a instruction add R1 comma R2. Here R1 and R2 are called as operands and add is called as opcode. Okay. The memory is organized into a group of n bits that can be stored and retrieved in a single basic operation. If we consider this as the computer memory, so this is called as a group of n bits. We also know 1 byte is equal to 8 bits and a word will contain 16 to 64 bits. Okay, in this diagram here n, a group of n bits. Okay, this n bits is called as a word length, and this is how the words will be stored in the memory. The first word, second word, and like this it continues. Now the modern computers have word lengths typically range from 16 to 64 bits. Okay. Say suppose if the word length is of 32 bits. Here, this if we consider the word length as 32 bits, your n here is equal to 32 bits. So a single word can store a 32-bit 2's complement number or 4 ASCII characters, each occupying 8 bits. So this is shown in this diagram. If we say this as a one word, okay, the word contains, say suppose, usually it contains how much? 16 to 64 bits. For our example, we have considered 32 bits. So how these 32 bits are represented? These are represented in this way. So this is the bit 0, bit 1, likewise till bit 30 and 31. So altogether we have 32 bits. That means one word. Okay. The last bit, this is used for the sign bit, that is to hold the value 0 for positive number and 1 for negative numbers. Either it can be in this fashion or it can hold 4 ASCII characters. Okay. Now each ASCII character will hold 8 bits. That means this one word which is of 32 bits will occupy 4 ASCII characters. Okay. Now accessing the memory to store or retrieve a single item of information like either a word or a byte, it requires distinct names. You cannot just say to your computer that go and access or go read from this memory. So what you have to do, you have to give some name to it. Next we will see how this can be done. For that we have to learn the byte addressability. So we know that 1 byte is equal to 8 bits and one word equal to 16 to 64 bits. So it is not possible, okay, it is not possible to address each and every individual bit locations in the memory. For that what we do, we successive address refer to the successive byte location in the memory. So this assignment is used in the modern computers. So this assignment we call it as byte addressability. So for example, say the byte location have the address 0, 1, 2 like that. So if the word length of the machine is 32 bits, then the successive words would be located at the address 0, 4 and 8 like that. Each word would consist of 4 bytes. For example, like this one. Okay. The first word would be starting at 0th location. So this is 0 byte, first byte, second byte and third byte. Altogether we have 32 bits. The second word would start from 4, again 8 bits each. Then the third word would start from 8. Okay. Okay. Now you have a quiz. So this is very simple. Okay. 1 byte is equal to how many bits? Type in your answers and your time starts now. Okay, time's up. Next, we'll see the two variations of byte addressability. That is, how a word and a byte would be addressed in the memory. So there are two variations of it. One is big endian assignment. The other one is little endian assignment. So if you see this diagram here, so here the bytes. So the zeroth word would be divided into 4 bytes. So the first byte we access it by zeroth byte location. Next is byte 1, next is byte 2, and the last one is byte 3. So after this, the location would start from the 4. Okay, again, the byte locations would be 4, 5, 6, 7, and this continues. Here, the big endian system, what it does is when it is used whenever the lower byte addresses are used for most significant bits. So if you consider here the lower byte address, we call it as 0, 4, 8. These are all lower byte address because if you see here 0, 1, 2, 3, which is the lowest one? 0, right? So this lowest byte address is used for the leftmost bytes or the most significant byte. So this is most significant byte and this is least significant byte. Okay. So big endian says whenever lower byte addresses are used for most significant bits of the word. Now, the opposite of this is the little endian. Here, what happens? It is used whenever the lower byte addresses are used in the less significant bit. Okay, the difference here is here it would start from the byte address would start from 0, 1, 2, 3, and here the opposite of this. Okay, 0, 1, 2, and 3. Again, both little endian and big endian assignments used in commercial machines. So in both cases, what happens? The byte addresses 0, 4, 8 are taken as the address of the successive words in the memory, and these are used for specifying the memory operations like read and write. In addition to specifying these address in the bytes of within a word, it is also necessary to specify the labeling of bits within the byte or a word. Okay. Next, we'll see the word alignment. So, in the case of 32-bit word length, the natural boundaries occur at the address 0, 4, 8. So, if you see this diagram, it is the same. The natural word boundaries are 0, 4, then it would be 8, then it would be 12, like this. Okay. Now, we say that the word locations have aligned address. If they are at the successive boundaries, then we say that they are aligned. So we say that the word is aligned in memory if it begins at a byte address that is a multiple of number of bytes in that word, usually the power of 2. So hence, if you consider the word length is 16, that means 2 bytes. So the aligned word address would start from 0, 2, 4, 6 like this. If the word length is 64 bits, that is 8 bytes, then the address would start from 0, 8, 16 like that. So there is no hard and fast rule that it has to be started from this particular address itself. So the it can have words can have unaligned addresses as well. So while the most common case is to use the aligned address, some computers do allow the unaligned word addresses. Next we'll see how to access numbers, characters and character strings from the memory. Okay, first we'll see about a word. Okay, a number usually occupies one word. It can be accessed by specifying directly the word address. So this is direct, straightforward. For characters, it can be accessed by their byte addresses. Now the problem is with the character strings. That is, say suppose your name is Harry, how to access this one, right? Where the string ends, how the memory should understand it. So the beginning of the string is indicated by giving the address of the byte containing the first character. Then successive byte location contain the successive characters of the string. Then how does the memory will understand that? Okay, this string ends here. This is the end of the string. So there are two ways to indicate the length of the string. So one is using a end of string, a special character to indicate that this is the end of the string. It can be used. Or the another method is to use a separate word location or a processor register, that is R0, R1 through Rn minus 1. One of these that contain the number indicating that this is the length of the string in bytes. Okay. Next we will see the memory operations. Okay. So this you already know that memory stores the programs, instructions, these all things, right? And we have also seen the connection between the processor and the memory in our first chapter. So there are two basic operations that are involved in the memory, that is load and store. Okay. Now this load operation is also called as read or fetch. Store is also called as write operation. Now we'll see how this load and store works. Okay. The load operation, what it does, it transfers or copies the content of a specific memory location to the processor. The memory contents remain unchanged here. So we already know, suppose if this is your memory and this is your processor, we know the connection between them, right? We have MAR, MDR, PC, IR, all these things, right? So what happens? So whenever you want to read something from the memory, suppose from this location you want to read something. So while reading, you do not change the content of it. You just copy it or you just read it, right? The memory content remain unchanged. Now how this load operation would start? For that, the processor, what it does, it sends the address of the desired location to the memory and the contents are then read from the memory. Now the memory reads the data stored in that address and sends them back to the processor. So this is the load operation. Next is the store operation. That means you have performed some addition or subtraction. You have done something in the processor. Now you want to store back it to the memory. How this is done? So the processor sends the address of the desired location to the memory together with the data to be written into that location. Getting it? Okay, next is another quiz. Say true or false. The store operation transfers a copy of contents of a specific memory location to the processor. So you have got 2 minutes of time and your time starts now. Okay, time's up. Next, we will study about instruction and instruction sequencing. Now, the task carried out by a computer program consists of sequence of small steps. Okay, a computer program consists of sequence of small steps such as adding of two numbers, testing for a particular condition, reading a character or sending a character to the display or printer. Now, the computer must be capable of performing basic four type of operation. The first one is data transfer between the memory and the processor register, arithmetic and logical operations on data, program sequencing and control, then IO transfers. So let us first begin discussing the first two types of instructions. Okay. So before jumping into this, we should know some basic notation. So we'll see that first. First one is register transfer notation. Now, what happens here is whenever there is a memory location involved in the uh, transfer, suppose, so what we do is we should identify that particular memory location. Say suppose we have a instruction add location A comma R1. Now this location A is a memory location. Now, how do you identify this memory location? You cannot tell the computer simply like go to this particular location, go to the location 0001 and add the contents, right? You should use some symbolic name. so that it is easily understood for you. Okay. Now for this, how a naming convention is done in the memory. So the names for the address of memory location, it may be some variable or symbolic name such as LOC, that is location, or it could be a word as place, a variable A or var2. Now these are some variable names, symbolic names. Okay. Now these things will be used for the address of memory locations. Now suppose you want to use the processor registers. So we know there are n general purpose registers in the processor. So the register's name could be RU, R1, R5, R0, etc. Apart from that, IO register names can also be used for IO systems such as data in, data out, or out status. Now, say suppose we want to move the content of a memory location to a register. How do we do it? So we represent like this. That is, LOC is a memory location. Now you want to move the content of this location LOC to the register R1. Okay, to the register R1. So what you have to do is, if you just write LOC, give a arrow mark and R1, this does not represent anything. It just says the memory location is LOC, then you have to move it to R1. But how do you represent the content? So if you want to denote the content of that, then you have to place the square brackets around the name of the location, just like this. Now this square brackets LOC, this represents the contents of the location, content of the memory location LOC should be moved to the processor register R1. Okay. We will consider another example wherein we want to add two numbers. Say that the two numbers are present in the registers R1 and R2. Now the content of R1 and R2 should be added and it has to be moved to R3. Now what do we do? Just what we have to do? We have to place the square brackets around the register names, that is like this. Okay. It says content of the register R1 should be added with the contents of the register R2 and the result has to be moved to R3. Now this we call it as a register transfer notation. Now the right hand side, it always denotes a value, and the left hand side, it is the name of some location or the register. Now what happens in this case is, whenever you add the content here, right, the content of the location R1 and the content of the location R2, the result will be saved to R3. Now we should note an important thing here. So if suppose the register R3 contains some value, that will be overwritten by this value. So what happens, say suppose register R1 is having a value 5. Okay. Then we have register R2 which has a value 10. Okay. Say suppose R3, it contains value say 20. Okay. Now once this operation is performed, it says the content of R1. Now the content of R1 is 5. Next the content of R2, that is 10. These two have to be added. So the sum is here 15. Now this 15 has to be placed in R3. So what it does? The content will be this sum 15 would be placed in R3. Now we should note that the existing content is overwritten by the new value. Okay. Remember, the existing content would be overwritten with the new value. Next, we will see about the assembly language notation. This is another type of notation to represent machine instructions. Say suppose we want to move the content of the memory location to a register. Now what do? We write an instruction saying move LOC, R1. This LOC is a memory location, R1 is a processor register. Now say suppose this location, okay, this memory location, it contains a value say 5. Now what happens is, when this instruction is executed, the contents of LOC will be transferred to R1. And say suppose R1 previously was containing a value 2. Once this instruction is executed, this 2 will be overwritten with a new value 5. Remember, the location value, this location content is unchanged. only the R1 value would be overwritten. Take another example wherein you want to add the two numbers which are present in the registers and you want to place the sum in R3. For that, how do you write it in a single instruction? You just mention add R1, R2, R3. Now the contents of R1 and R2 will be added and it is placed in R3. Now R3 contents would be overwritten but R1 and R2 would be remain unchanged. Okay. Next we will see the basic instruction types. Consider the command C is equal to A plus B. What it says is the content of the variables A and B should be added and the sum has to be placed in the variable C. Now we should understand when this statement is compiled, what happens is three variables are assigned to distinct location in the memory. Suppose if we consider this as our memory, okay, so A could be somewhere here, B can be somewhere here, and C can be somewhere here. Okay, now these could be A, B, C. These variables can be present anywhere in the memory. So the contents of this has to be added. Now what do we do? To understand the contents, what are the contents of the memory locations A and B? So we have to place the square brackets like this. So once this is done, so what happens is the system understands that the contents of the A and B has to be added and it has to be placed in C. Now say suppose A contains the value 1 and B contains the value 2. So whenever this statement is executed, so the contents of A and B are added and placed in the location C. Okay. That's it for today. We'll conclude our session. Thank you. Next, we will see about the different types of instructions like 3 address, 2 address, and 1 address. First, we will discuss about the 3 address instructions.